Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to be going over molecular orbital diagrams involving the second row diatomic molecules, in particular the homonuclear diatomic molecules. So let's get into this. So if we combine the splitting schemes of the 2s and the 2p orbitals, we can predict the bond order in all of the diatomic molecules and ions composed of elements from the first complete row of the periodic table, which is the second row. Now, what that means is, if you remember from the previous videos, I showed the splitting diagram of the s orbitals, right? So you get the s orbitals combined to get you the sigma 1s and the sigma 1s star molecular orbitals, right? So you get that splitting. And I also showed you the splitting with the p orbitals, right? The 2p orbitals or the np orbitals, and how you can get the sigma pz bonding orbital, and you can get the sigma pz star antibonding orbital, and then you get the pi bonding and antibonding orbitals as well. Well, we could take both of those and put it together, and then we could use that to do the to predict the bond order of the diatomic molecules of those of that row of elements, the second row of elements. So the other thing to remember is that only valence orbitals really need to be considered in this. So if we're in the second row, that'll be the 2s and the 2p. There's no reason to consider the 1s because that's more of a core inner orbital, and the inner orbitals are going to remain tightly bound, and they're going to retain their localized atomic character. So they're not going to become molecular in the sense that those electrons are sheared by the atoms in the whole molecule, but rather they're going to be localized to whatever atom has those electrons, those inner orbital electrons. And again, in this video, we're going to describe examples of systems involving the period 2 homonuclear diatomic molecules. That would be like N2, O2, F2, and so on. You have carbon as well, and beryllium. And so I'll save for another video the heteronuclear diatomic molecules. Hetero meaning different, so that would be like NO together, NF or OF or things like that. So we'll consider those sorts of molecules in a different video. When we are drawing a molecular orbital diagram or energy level diagram for a molecule, there's four key points that you want to remember. And you'll remember I covered these in another video, but I didn't really list them, but I'm going to list them here. So the first thing is the number of molecular orbitals. MO means molecular orbital, and AO, it means atomic orbital. So the number of molecular orbitals produced is the same as the number of atomic orbitals used to create them. So this is also known as the law of conservation of orbitals. So what you put in is what you get out, right? So if you put in, this is pretty similar to the hybridization, right? If you take an S and a P and you combine those together, you get two sp hybridized orbitals. But this is not hybridization in that sense. This is, molecular orbital theory. Hybridization was from valence bond theory, but the idea is the same. So if I combine my atomic orbitals, so if I take two s orbitals on two different molecules, that's the difference between the valence bond theory, right? In valence bond theory, you're taking an S and a P or whatever from the same atom, and you're hybridizing those together. In molecular orbital theory, you're taking the atomic orbitals of different atoms and combining those together. So you take a 1s from one atom, a 1s from another atom, you combine those, you get two molecular orbitals, you get the sigma 1s bonding orbital, and you get the sigma 1s star antibonding orbital. So you get two molecular orbitals from two atomic orbitals, right? If you had three or four, if you had like say four atomic orbitals that you're combining, then you're going to get four molecular orbitals from that. So the second one is as the overlap between the two atomic orbitals increases, the difference in energy between the resulting bonding and antibonding molecular orbitals increases. And we saw this in a previous video. So you'll see that from the p orbitals, right? The overlap of the p orbitals. The p orbitals that are internuclear, that overlap internuclear, they're going to have more of an overlap. And so, therefore, that's going to give rise to the sigma pi ps, or I'm sorry, pi pz bonding molecular orbital, and the I'm sorry, I shouldn't say pi, sigma, because we're talking about the internuclear axis. So along the internuclear axis, if the overlap is there, we call those sigma. So I misspoke. So the overlap of the pz orbitals on the adjacent atoms is going to give rise to the sigma pz and sigma pz star molecular orbitals. And the distance between them, the energy distance between them, is going to be pretty large. But if you have the p orbitals like the px and the py that are perpendicular to the pz, their overlap is not going to be internuclear but outside the internuclear axis, so you don't get as good overlap. And then the energy difference between your bonding and antibonding molecular orbitals is going to be less. It's going to be they're going to be closer together. And again, I'll show you an orbital diagram, and I'll point that out in a moment. When two atomic orbitals combine to form a pair of molecular orbitals, the bonding molecular orbital is stabilized about as much as the antibonding molecular orbital is destabilized. So remember, the bonding orbital has a stabilizing effect. The antibonding orbitals, molecular orbitals, have a destabilizing effect. And so what that means is we're talking about when you stabilize something, it's lower in energy. If you're destabilizing something, it's going to be higher in energy, right? So what that means is when you are creating molecular orbitals from equal energy atomic orbitals like 1s and 1s, right? So you have the 1s orbitals that are at the same level, right? If they combine forming a bonding molecular orbital, well, that molecular orbital is going to be lower energy, and that's going to be stabilizing. And then you're going to have them come together in a destructive way. And so when they come in a destructive way, that's going to be destabilizing. And then the molecular orbital that results from that is going to be higher in energy and therefore destabilizing. So the amount of energy that's raised, the amount of energy that the bonding orbital goes down is going to be about the same as the energy of the antibonding orbital goes up compared to the whatever the energy level is at the for the atomic orbital. So we're comparing this to the energy level of the atomic orbitals that are being used. Okay, and then finally, the interaction between atomic orbitals is greatest when they have the same energy. So when orbitals have the same energy, the interaction between the atomic orbitals is greatest. If they don't have the same energy, then the interaction is not going to be as great. So that's going to. These are four key things to keep in mind when you're doing or making or drawing your molecular orbital diagram. Okay, so now let's go into showing and talking about a molecular orbital diagram for a homonuclear diatomic molecule. And we'll start with fluorine, and we'll do oxygen as a comparison. So stay tuned. Okay, here we are with our molecular orbital energy level diagram. Notice that I have the splitting orbital level energy level diagram for the S's here, and I have the P's up here, so I've added those together. And so this is the orbital diagram, the energy level diagram that we can use for fluorine and oxygen. So just like before, we have the atomic orbitals of the atoms on the side here, and then we have the molecular orbitals in the middle. And you'll notice that by adding these two together, we get two molecular orbitals, bonding, anti-bonding. We have 1, 2, 3, 1, 2, 3, that's 6. We combine those 6 and we get 3 bonding molecular orbitals and 3 anti-bonding molecular orbitals. So I covered this in earlier videos, so we're just kind of putting it together. And so now what we can do is we can fill in the electrons into the atomic orbitals, and these are valence orbitals, so we're only considering the valence electrons. So as you know, fluorine is in group 7, so it has 7 valence electrons. So let's go ahead and fill that in. So we're going to use all the principles, Aufbau principle, Hund's rule, and all that, right? So Pauli exclusion principle. So we have 7 electrons, so we're going to put spin up, spin down here. And then we got 3 equal energies, so Hund's rule, so spin up, spin up, spin up, that's 5. And we got 2 more, spin down, spin down. So that's this fluorine atom, and it's the exact same thing for this fluorine atom. So spin up, spin down, spin up, spin up, spin up, spin down, spin down. Okay, so now we have our atomic orbitals filled. So now we're just going to take all of the valence electrons and fill them in from top to bottom. So we're going to follow Aufbau principle. We're going to follow Hund's rule. We're going to follow the Pauli exclusion principle as we fill in the molecular orbitals, just like we do with the atomic orbitals. So here we have 7 plus 7 is 14. So we fill everything in with 14 electrons, starting at the lowest energy. So this molecular orbital gets 2 electrons, spin up, spin down. That's full. We go to the next one. This molecular orbital gets 2 electrons, spin up, spin down. That's 4. We got 10 more. So now this orbital is the next one higher. So spin up, spin down. And now we can fill in this. Now notice that they're equal energy. So we do Hund's rule. So we fill them in one at a time. Spin up, spin up. And then we pair them together. Spin down, spin down. So far we've used up 2, 4, 6, 8, 10 electrons. We have 4 more. So now we filled in the bonding orbitals here. Now we're going to start to fill in the anti-bonding orbitals. We got 4 more. So again, equal energy means we fill them in one at a time. So spin up, spin up. We got 2 more. Now we pair them, spin down, spin down. So that's all 14 electrons. So this is what the molecular orbital energy level diagram would be for F2, right? So we could write the electron configuration for F2, right? So that would be, starting at the bottom, it would be sigma 2s with 2 electrons, followed by the sigma 2s star with 2 electrons, followed by the sigma 2pz, right? So we have the sigma 2pz with 2 electrons, and then we got the pi 2px, pi 2pz. So here would be pi. We could do pi p x, I guess, with 2 electrons, followed by the pi py, 2 electrons. Or another way you could do it is you could just combine it, right? and this could be 2pxy with 4 electrons. And then you just keep going up. So you could write out the electron configuration for F2. For the bonding, we can figure out the bond order, BO for bond order. So remember, it's the number of bonding electrons minus the number of anti-bonding electrons, and then that difference is divided by 2. So the number of bonding electrons are the electrons in the bonding molecular orbital. So we have 1, 2, 3, 4, 5, 6, 7, 8. So the bonding molecular orbitals are those that do not have a star. So again, 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be equal to 8. So we have 8 bonding electrons. Now for the anti-bonding electrons, those are going to be the electrons that are in the molecular orbitals with a star. So we have 1, 2, 3, 4, 5, 6. So we're going to minus 6, and then that is divided by 2. 8 minus 6 is 2. So 2 divided by 2 is 1. So the bonding order is 1 for F2, which is fits with our data and what we know about F2. So that does have a single bond. So that is correct. Now, what about oxygen? So we could do the same thing for oxygen. Oxygen uses the exact same energy level diagram, the molecular orbital energy level diagram, so there's nothing to change. The only thing that changes is the atoms, the molecule, and the number of electrons. So if we just change this to an O, change this to an O, and then change this to O2, like so. And the only difference is the number of electrons. So oxygen is in group 6, so it has 6 valence electrons. So we're going to have to get rid of an electron here, right? So we have less electrons paired up. So this one is gone like so. So this is the number of electrons. This is the energy level diagram for an oxygen atom. And so when we fill this in, we have 2 less electrons. So that means that these 2 highest are not going to be paired up, right? Because we lost 2 electrons. Those are going to be unpaired. So again, remember Hund's rule. So you fill them in one at a time before pairing them up. But this time we have 2 less electrons. So we don't have any electrons to pair these up. So these 2 are going to be split into the equal energy orbitals, the molecular orbitals. So now you can see here that again, we could write the electron configuration for this. We could do the bond order. Let's do the bond order for oxygen. Again, the bond order is going to be equal to the number of bonding electrons minus the number of anti-bonding electrons. That difference is divided by 2. So again, we have 1, 2, 3, 4. Oops, not that one. That's a star. That's not bonding. So this is bonding. 1, 2, 3, 4, 5, 6, 7, 8. And we're going to subtract the anti-bonding electrons. So we got 2 here. And then we got 2 there. That's 4. And then that difference is divided by 2. 8 minus 4 is 4. 4 divided by 2 is 2. So in this case, the bond order of oxygen is 2, meaning it has 2 bonds. It's a double bonded molecule, again, which fits with our data that we know about the bond strength and the bond length in the oxygen molecule. Now, there's one thing, or there's a few things that we're going to talk about next. Is this orbital diagram gives us more information and predicts things about oxygen that we know to be true that valence bond theory and Lewis dot structures do not do not tell us. So we can't predict it from valence bond theory or from the Lewis dot structure. And one of those things is paramagnetism. So, and there's a few other things, so I'll talk about that next. So stay tuned. Okay, so let's talk about the property of oxygen. So as you can see that from the molecular orbital diagram, we see that we have unpaired electrons. You don't get this when you do your electron configuration for oxygen, or if you do valence bond theory, or if you do Lewis dot structure, you'll have the electrons all paired up in each case. This is the only case in which you end up with two unpaired electrons, and therefore making this paramagnetic, which means that we would predict that oxygen molecule has magnetic properties, and this is exactly what we observe. So this was a kind of a confusion or something that was befuddling scientists, is to understand, well, how is it that the molecule oxygen can have these molecular properties? You saw with fluorine that we had those two extra electrons, so everything was paired up, and so you don't see fluorine having magnetic properties. So we do see oxygen molecules having magnetic properties. You can actually suspend liquid oxygen between two magnets, and you can let it boil off and vaporize while it's suspended in air between those two magnets. How is it that oxygen does this? Well, the conclusion is that it must have unpaired electrons. And so molecular orbital theory was able to kind of show that and present the argument. This is important also for life, right? So we see that oxygen, our atmosphere is made up of about 20% oxygen. Oxygen could react, would react with other organic materials, right? And then, to make water and other substances. So living organisms like you and me and plant life and all the rest of it would react completely with the oxygen in the air if it wasn't for the fact that we have two unpaired electrons, and then all the other organic molecules actually have paired electrons, all paired electrons. And so that would require, in order for oxygen to react with other organic molecules, it would require at least one of the electrons here to flip its spin, to change its spin, and that would require a large amount of energy, a relatively large amount of energy to do that, and that's called the spin barrier. And because of that spin barrier, the reaction with oxygen, the reaction of organic molecules with the oxygen molecule in the air is relatively very, very slow. And so that's one of the benefits of having unpaired electrons in your oxygen. Okay, so the other thing I want to talk about lastly is the ordering of the molecular orbitals. This ordering of molecular orbitals is not the same for all molecules in the period 2 elements, of the period 2 elements. We looked at oxygen and fluorine. This ordering of the molecular orbitals actually only applies to oxygen and fluorine. If we're going to look at nitrogen, like N2 and C2 and B2 or BE2 and the rest of it, the ordering is slightly different. So let me talk about that. So stay tuned. Okay, so let's talk about this difference in the molecular orbital energy diagrams for the second row, or second, I should say, second period molecules. And so what you see here is just a simplified version of the molecular orbital energy diagram. So here this is the molecules for the elements, so lithium to beryllium to boron to carbon, all the way to fluorine. And so here's the order of the energy diagram. So here's oxygen, fluorine that we looked at, and here's the ordering of the molecular orbital diagram. So we have the sigma 2s, so sigma 2s, sigma 2s star, and then we have the sigma 2pz, and then we have the pi 2px and 2py, and then we have the pi 2px and 2py, the star, pi 2px star, 2p, the pi 2py star molecular orbitals, and then we have the sigma 2pz star, excuse me, star or molecular orbital. And here, so for the oxygen and the fluorine, you can see that the sigma 2pz is lower in energy than the pi 2px and the pi 2py orbital molecular orbitals, and we saw that earlier. So so the pi 2pxy antibonding and bonding molecular orbitals are between the sigma 2pz and the sigma 2pz star bonding and antibonding orbitals. So this is the order of the molecular orbitals for oxygen and fluorine, but you'll notice that for the rest of these, from lithium to all the way to nitrogen, these two are flipped. So the sigma 2pz molecular orbital is higher in energy than the pi 2px and pi 2py degenerate molecular orbitals. Degenerate meaning that they have the same equal energy. And so you'll see that from here on out, the 2pz molecular orbital, the sigma 2pz molecular orbital is higher in energy than the 2px, 2py, the pi 2px, 2py molecular orbitals. And that stays that way until you get here. So in the transition from N to O, they flipped they flip, right? And so what's the reason for this change? Well, what happens when you go across the period in the periodic table? We know that the effective nuclear charge increases, meaning that the nucleus, the charge, the positive charge in the nucleus increases. And so what happens is that when we're looking at the atomic orbitals, right, the atomic orbitals, S and P, they're going to increase in the difference in energy. So the difference in energy of your S and P orbitals, the atomic orbitals, are going to increase. And so there's a phenomenon referred to as SP mixing. And so when the S and P orbitals are relatively close together in energy, then you start to get what is called mixing together, where they kind of interact more with each other. You can't so normally what we do is we assume that when you form molecular orbitals, you got one S over here, you got one S over here, and just those two are interacting to form the two molecular orbitals. If you've got a P and a P, right, those are the only two that are going to form, and you get two molecular orbitals from that. So the S is not going to be involved with the P is not going to be involved with the S. But that's assuming that the energies are relatively far apart, right? So if the S and P energies are relatively close, then that is not going to be true, right? So this is where you get the mixing, the S&P mixing. So you're going to have some S&P mixing here because on this side um, the nuclear charge is not very large, right? Relatively small. So the energy differences between S&P atomic orbitals are going to be closer. Therefore, you're going to have more SP mixing. And so that's why the sigma 2pz is going to be higher in energy than the pi 2pxy orbitals. Now you could see as you go across, the sigma 2pz is going down dramatically in energy, where the pi 2pxy molecular orbitals are going down a little bit, but slightly, very slightly. So as you go across, the S and P orbitals are getting larger in energy, so you're not going to have as much mixing. And so you get this phenomenon here where eventually when you get to oxygen and fluorine, these guys flip sides. And so when we're writing our molecular orbital diagram for our diatomic molecules, right, we got to know which molecular orbital diagram to use, right? So if we are doing the molecular orbital diagram involving oxygen and fluorine, we've got to use this ordering of the molecular orbital diagrams. And so the pi 2px and y molecular orbitals are going to be higher in energy than the sigma 2pz molecular orbital. But if we're doing nitrogen, carbon, bromine, beryllium, and lithium, then we got to make sure that we're using this order where the pi 2px and y molecular orbitals are lower in energy than the sigma 2pz molecular orbital. And so that's what you got to keep in mind. And also when we talk about heteronuclear molecules, diatomic molecules, you'll have to worry a little bit about this as well. But that's it for this video. I hope you enjoyed the video. I hope this was insightful. I hope this helped you. If you enjoyed the video, if this helped you in any way, then please like the video, share the video, hit that like button over here somewhere. Also, do me a favor, subscribe to the channel, help me out. I need your help. Well, you don't have to, but I would really love it if you did. And then finally, put a comment down below in the comment section. I would love to hear from you. If you have a question or a comment, put that down below. If you have a problem or a question that you need help with, if you have a topic you need help with, put that down below. I would love to help you with that. Thanks for joining me and have a great day.